Exercise 5. This is the last one. So this is a rather simple exercise. First, we will solve it. We'll find the exact solution via some probability steps, so analytical steps, and then we will try to get an estimate of the same solution via computer simulation. Let's read the question. Consider two battery-powered watches and let x1 denote the number of minutes past the hour at which the first watch stops, and let x2 denote the number of minutes past the hour at which the second watch stops. What is the probability that the larger of x1 and x2 will be between 30 and 50? Okay, so we have two random variables, x1, x2, that represent the minute past the hour at which each of these two watches stop. So these two numbers will be between 0, 1, 2 and 59, right? Because like it can't be 60, it will be the next hour. So we don't have any reason to think that one watch has got a higher probability to stop at a certain at a specific minute past the hour. Watches, I mean the battery inside the watches is supposed to last for months or years. So really, we'll assume, and it's reasonable to assume, that every minute is equally likely. So x1 and x2 are in fact uniform distribution on the set of numbers, of integers from 0 to 59. Great. So what we are asked to find is the probability that the maximum between x1 and x2 will be between 30 and 50, and we can include the extremes. Okay. So sometimes when we have to calculate the maximum or minimum of the random variable, of two random variables or more than two, you have to play a bit with the event. So there are many ways to do this. This is a possibility. So for example, we can consider the probability of the complement. So this probability is equal to 1 minus the probability that the maximum will be strictly lower than 30 minus the probability that the maximum will be strictly higher than 50. Okay, so maybe I've done two steps in one, but it's clear that these two events are disjoint, and therefore the probability of the intersection is equal to the sum of the probability of the two events. So let's calculate this. So it should be clear that for the maximum of x1 and x2 to be lower than 30, I really need both these variables that are independent to be lower than 30. They are independent, so I want x1 to be lower than 30 and x2 to be lower than 30. Okay, and this is equal to so any number from 0 to 29 will be fine. There are 30 numbers out of the 60 minutes in an hour. Okay, and very similarly we can solve also the other probability. So this will be 1 minus the probability that the maximum between x1 and x2 is this will be lower or equal 50, right? So we have to be careful here, and then we can solve this the same way as with the 30. So this will be 1 minus, both of them have to be lower or equal than 50. So any number from 0 to 50, there are 51 numbers. So 51 over 60 squared. Great. So the probability that we are searching for will be 1 minus 30 over 60 squared minus 1 plus 51 over 60 squared. And this is equal to 51 over 60 square minus 30 over 60 square, which is exactly, okay, we need to use, I don't know, a calculator or R, 0.4725, and this is the solution. So this is the exact solution that we found analytically. All right, and now we'll move to RStudio to solve the same problem but with a very different approach, with the computer simulation. Okay, here we are. Welcome to my RStudio interface. So as you can see, I've collected here all the calculations that we have done with the different exercises in this video, so you can have a look and make sure that everything makes sense. Exercise 1, 2, 5, and the last exercise will fill it together. Okay, so yeah, so this is optional. Okay, this part of the exercise is optional. There are some commands that you've seen already, such as the command sample. However, there are also other commands, such as pmax, that probably we won't need in the future, and you're not expected to remember these commands. Okay, so this is optional, however, very useful, especially like, I don't know, this is something very powerful that you can do with computer simulation. So, let's recap the exercise. We had 2 watches and like battery powered, and each of these would stop us a minute past the hour. Okay, so x1 is the minute past the hour for the first watch stops, and x2 refers to the second watch. And we want to compute the probability of the maximum between x1 and x2 to be between 30 and 50 minutes. So we actually found the exact probability, which was, if I remember correctly, 51 over 60 square minus 30 over 60 squared. Okay, so you can run this code to check what's inside. Okay, you can do this in many ways. So for example, you can write exact here, compile 0.4725. This is great. Okay, so many times in real world you have a problem that so in this case we could solve it through some probability and analytical steps. However, many times in real life you either can't solve it in a mathematical way, or you just like, it would take just like too much time to solve it in a mathematical way, to search for the solution. And a very valid alternative and very powerful alternative is to use computer simulation. This is a very powerful technique that goes under the name of Monte Carlo methods. Okay, these methods consist of solving analytical problems through computer simulation. So let's look at an example of this. So the idea is to simulate the scenario many times. So we can simulate 2 watches, check when they stop, compute the maximum of the minimum past the hour, and then see whether this maximum belongs to the interval 30-50. Okay, and we can do this many times. So in order to get an estimate of the probability for this maximum of x1 and x2 to be between 30 and 50. So hopefully it will be clearer once we actually do it. So first of all, we sample from the first, from x1, so the first watch, n times. We will start with a very low n equal 10. So we will sample from x1 n times. In order to do so, we need to use the function sample, okay? We sample from 0 to 59, okay? We sample one number from the set 0, 59. How many times? Size equal n, 10 times. We want to be able, we have this parameter replace equal true, because like it is actually possible that in our simulation that a watch stops on the 33rd minute past the hour more than one time, right? So this is draw with replacement. We are drawing from 0 to 59. So let's see. x1, so let's see what x1 looks like. So the first, so we have simulated this the battery and this from this x1, right, 10 times. The first time was 4, then 42, 21, 42, and so on. Of course, we can do the same with the second watch. Okay, and so we have sampled the scenario, okay, of the two watches stopping times 2 times. If you use the command setSeed1, right, and then you compile these two lines, you will get the same result as I do. So I'll just like run the setSeed1, x1 and x2. So let's compare x1 and x2. Okay, so in the first scenario, the x1 is 56 and x2 is 50. Second scenario, we have 3 and 32, and so on. So we have like 10 different scenarios. What we're interested in, so the first thing is to compute the maximum of these two numbers each time, okay? As that's what we want to check whether it belongs to interval 30, 50. So in order to do so, we can use the function Pmax. So we will define the maximum of x1, x2 using Pmax of x1 and x2. Okay, the function Pmax, you don't have to remember this, however, it's useful at times. If you input two vectors, okay, with the same length, the function will compare each entry, each corresponding entry, and pick the maximum. So let's run this function, and now we want to see what's inside x1, x2, and the maximum. Let's see if we did the right thing. So in the first scenario, we had x1 56, 50, and the maximum is 56. That's great. 3, 32, 32, great, and so on. So this function seems really to be doing what we wanted. Okay, so we have the maximum. Now, every time, for every scenario, we want to check whether this maximum belongs to the interval 30, 50. Okay. First, we will define a logical vector larger or maybe greater, okay, 30. So this logical vector will compare the maximum with 30, okay? So the maximum can be, has to be greater, but it can also be equal to 30. So running this command, okay, you don't need the bracket, but I think it's more it's clear with brackets. You will define a logical vector, okay? And a logical vector is a vector of true and false. So for every entry, we will have a true if the maximum is greater or equal to 30, or a false otherwise. Let's see. Let's check what's inside max and greater 30. Okay, so first entry 56, true. Yes, in fact it is greater than 30. Also the second and the third entry are greater than 30, so we have true, true. The fourth entry is 20. This is not greater than 30, and indeed we have a false. We can use a very similar, we can use the same code, just like adapting, to check whether the maximum is lower, right, than 50. So run this line, then compare the maximum with the logical vector result, which is the result of the previous operation. 56 is not lower than 50, so we have a false. 32 is lower than 50. True, true, true. 41. Then we have a 53 here, and indeed the 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The sixth entry is a false. Okay. Okay. However, so now we have two logical vectors that tells us the first one whether the maximum is greater than 30, and the second one whether the maximum is lower than 50. So the final logical vector will check whether both conditions are met. And we can do this using the logical operator. Okay, this one, I think it's called commercial E, I'm not sure. Okay, so this operator, if it is used between two logical vectors, it will return true. So it will return a vector of the same length of these two vectors, and each entry of the resulting vector will be true if and only if both of the corresponding entries in these two vectors are true. Okay, let me show you. So let's display greater 30, lower 50, and logical. Okay, so the first entry is higher than 30 but not lower than 50. True, true results in a false. The second and the third entry are higher than 30 and lower than 50, and therefore the condition is met. So true, true gives a true. Logical is true, okay, only if and only if both of these values are true. So, like, not very many times. Okay, so to sum it up, this condition is to check maximum is greater or equal 30. This second condition is to check whether the maximum is lower or equal 50. And this is to check both conditions are met. Great. So, last bit. So, this is very intuitive. It can be proved rigorously with the weak law of large numbers. However, this is intuitive. So, we can simulate, we are simulating this scenario 10 times. On average, how many times the event has happened, so the event of this maximum to be between 30 and 50, we just have to count 1, 2, 3, 4. So in this particular case, it's happened like 4 times that our maximum was between 30 and 50 out of 10. So a rough estimate of the probability for this event to happen will be 40%. So, in order to calculate this, we have to just sum the truths and then divide by n. But a faster way to do this, estimate, will be just to compute the mean of the logical vector that we've defined. As if you treat a logical vector as a numerical vector, then the truths will be 1 and the falses will be 0. Okay, this is very useful at times. So we write our estimate and then we compare it with the exact estimate, with the exact solution. That's not just an estimate. Okay, so indeed we have 0.4, but the actual number is 0.47, so the exact. But we've only used 10 simulations, right? So if we increase this to 100, our precision will improve. Okay, that's not the case, but 100, it's still a very low number. Okay, hope that this works. Okay, finally we are getting there. So with 1,000 simulation, this seems to be getting closer. Of course, usually you won't have the exact result if this is a real life problem. However, we can compare it with the exact result in this case. Now, 1,000 simulations, maybe it seems a lot to you, but it's not at all. We can increase this to 1 million, and I'm sure it will take under 1 second to do this. Okay, more or less. So we have precision so we are correct up to the third decimal digit. So you can increase this further until so maybe with 10 million it will start to struggle a bit. Okay, so it's taking a few seconds, but no big deal. So we are getting close to the, this is the precision up to the fourth digit and so on. We clearly, for the law of large number, we have the convergence on this because we are computing an average. So we have convergence of this sample average to the true exact solution. This method, this method of solving like mathematical problems is called computer simulation, or also Monte Carlo methods. It's very powerful because like computers are getting increasingly powerful. So I don't know. I hope that you find this example interesting, and definitely you'll see some more of Monte Carlo methods, not in this module, not in this course, but in the future. Okay, that's it for today. I hope you find this video useful, and I'll see you in the next video. Bye bye!